Okay, so we're very happy to have Bellaouar Djamel here at MOPA to speak on some generalizations on the representations of unlimited natural numbers. And this is joint work with Dawood Abdul Majid. Go ahead.
Okay. Thank you very much for inviting me to do this talk in this seminar on models of piano arithmetic. So it's a great honor for me to present in front of you a modest work entitled some generalizations on the representation of unlimited natural numbers. Okay, let us start with the work plan. So as you see, there is an introduction and 5 sections. In fact, this study is a mixture between elementary number theory, algebraic number theory, and non-standard analysis, where we can study the arithmetic properties of unlimited integers. We mention in the same context, we mentioned from the literature the following published papers. Okay. Recall that any unlimited natural number is either of the form 1 or of the form 2. Here, there is a question. If n has the second form and we add to it an integer, positive or negative, what form is the result? This question was asked by Dawood in 2006 as this way. Based on some notions from elementary number theory as divisibility, Euclid's algorithm, the sum of squares, quadratic residues, distribution of primes, etc. We gave in this paper, several types of unlimited natural numbers that can be written as the sum of a limited integer s and the product of 2 unlimited integers. Okay, in the very nice paper of Karel Harbejek, who proved that there is an unlimited prime number p such that for any integer s, we have p plus s cannot be the product of 2 unlimited integers. So I gave the name for these primes by Harbejek's primes. We use this notation to say that A and B are of the same order, which means that the ratio A over B is appreciable. And here let n of t be the number of digits of the positive integer t. In this lemma, we give a necessary and sufficient condition for the unlimited integers A and B that having the same order, as you see in formula 2. For the proof, in the first sense, assume that n of A minus n of B is limited, and we prove the following inequalities. So look at this here. Because A is less or equals the number 9 omega times, and B is greater than the number 100 omega prime times, and so A over B is appreciable. For the converse, we use the proof by contradiction. So the ratio A over B cannot be appreciable when n of A minus n of B is unlimited. In this example, consider an unlimited number of this form. Okay, look, 111 omega times. So we can write this number as the product of two unlimited integers. Okay, this is omega 1 and this is omega 2. Here there is k times, and here k minus 1 times. And so we can write this number as omega 1 times omega 2 plus omega 3 times omega 4. This is the case when omega is even. In the case when omega is odd, we use the same procedure. In the previous talk of Karel Harvachuk, he proved that every unlimited integer omega can be written as this representation, where omega I and the square root of omega are of the same order. So in this theorem, we add two conditions. The first one is omega 1 and omega 3 are unchanged, that is, are fixed. And this representation holds for different ways. For the proof, consider P1, P2, and P3 three distinct unlimited primes, such that this condition. And consider the Diophantine equation P1x plus P2y equals omega. If we assume the solutions xt and yt are positive, then the variable t satisfies these inequalities. And the previous inequality, okay, holds for different many ways. Here, xt and yt cannot be both limited, and if we assume that xt is unlimited, we can show that yt is also unlimited. Okay, for the proof that omega I and omega j are of the same order, we assume that P1 and P2 are unlimited consecutive primes. And for some choices of t, we prove that P1 and yt are of the same order, and also P2 and xt are of the same order. And so xt and yt are of the same order. This is because by the prime number theorem, we have P1 over P2 is appreciable. Consider the following problem. Here omega equals n factorial, and here omega equals the product of the first prime numbers where Pn is unlimited. Okay, so the question is, without using Bertrand's theorem or Bertrand's postulate and Euclid's algorithm, we ask if we can find the factors omega 1, omega 2, omega 3, and omega 4 such that this formula 8, where omega I and omega j are of the same order. Also in the number 3, omega equals the product of the first Fermat numbers. So in this talk, we give a positive answer for 1 and 2, but 3 remains unsolved. More general, we consider an unlimited natural number of this form, okay, given by this product. Here, A1 is standard, A2 is standard, and AK is unlimited. Okay, K is unlimited, but we assume that the difference between two consecutive factors is limited. So we can write this number as the product of two unlimited integers having the same order. For the proof, at first we prove that there is a unique unlimited integer, positive integer t satisfies these inequalities, or equivalently, the inequality is 11. Okay, here we consider these reports. So since t is unlimited, then at plus 1 is unlimited, and 1 over at plus 1 is infinitesimal. Here we distinguish three cases when this report is appreciable, infinitesimal, and unlimited. In the first case, when this report is appreciable, okay, since the difference between two consecutive integers is limited, then there is an unlimited I0 such that AI0 and the square root of t plus 1 are of the same order. And here we put R1 by this number and R2 by this number. It's clear that n equals R1 times R2, and the ratio, this ratio is appreciable because it's the product of two appreciable numbers, this one and this one. We have the same when the report is infinitesimal and when the report is unlimited. Okay, there are some differences in the proofs, but for each case we obtain that n can be written as the product of two unlimited integers having the same order. Okay, now in this corollary we deduce that if n given by this form, then n can be written as omega 1, omega 2 plus omega 3, omega 4, where omega I and omega j are of the same order. The proof is quite simple, and in the next corollary, consider the number n factorial. So n factorial can be written as the product of two unlimited integers having the same order, and so we can write n factorial as this form. Okay. In the next corollary, we consider a number given by this product, but here we assume that any two consecutive factors are of the same order, not as the difference. Here we assume that AI plus 1 over AI is appreciable. Then by using the same procedure as the previous theorem, we can write this number as the product of two unlimited integers having the same order. There is some questions in this section. Okay, the first one, as you know, any unlimited positive integer can be written by using digits. Okay, here d1 is different from 0, but the others are from 0 to 9. Okay, so without using Bertrand's postulate and Euclid's algorithm, we ask how to find the factors omega 1, omega 2, omega 3, and omega 4 such that n equals this writing, omega 1, omega 2 plus omega 3, omega 4. But we assume that the difference between n of omega I and n of omega j is limited. The second question, we don't know if there is an unlimited prime number such that this representation and the factors omega I satisfy these conditions. And in the third question, we assume n is given by this product, but here for I unlimited, when the index is unlimited, then AI and AI plus 1 are not of the same order, as we have seen with the product of Fermat numbers. So here we don't know if n can be written by this form without using Bertrand's postulate and Euclid's algorithm. Okay, now we talk about the representation of unlimited matrices with integer entries. So we need to define an unlimited matrix, and we ask the general question if any unlimited matrix with integer entries can be written as this form, where S is limited and omega 1, omega 2 are two unlimited matrices. We try to construct a matrix of this form, and we show that this matrix can be written as the above formula, that is as S plus omega 1, omega 2. Okay. Let n be an unlimited integer given by its canonical factorization. And consider the quadratic equation x squared is congruent 1 modulo 9, modulo n. Then this equation has R solutions, and these solutions satisfy the following properties. For example, if we take n equals 6, then we find C1 equals 1 and C2 equals 5, because 1 squared is congruent 1 modulo 6, and 5 squared is congruent 1 modulo 6. Okay. And using the previous solutions, we define the following matrix C given by this form. Okay. And we prove that C is unlimited, and C can be written as the sum of a limited matrix S and the product of two unlimited matrices with integer entries. Here, omega 1 is diagonal. Okay. For the proof, by using the properties of the previous solutions, we can write C as this form. Okay. This is S, this is omega 1, and this is omega 2. It remains to show that omega 1 is unlimited and also omega 2 is unlimited. For omega 1, this is clear because the prime powers, at least one of the prime powers of n is unlimited, and so this matrix is unlimited. It remains to prove that omega 2 is unlimited. Here, there are several cases. In the case when P1 to the alpha 1 is limited, then we show that this matrix is unlimited because C2 and C3 and etc. up to CR are unlimited. Okay, and in the case when all the prime factors of n are unlimited, here we distinguish two subcases. When the number of prime factors of n is limited, so we use the following congruence equation, because in the case when n equals 6, we have 1 plus 5 is congruent to 0 modulo 6, because 6 equals 2 times 3. And the next case, in the case when the number of prime factors of n is unlimited, okay, we can show that the matrix omega 2 is unlimited. Okay, in this theorem, we prove that any m by n integer matrix, limited or unlimited, can be written as the sum of S plus omega 1, omega 2. For the proof, we take as any non-zero matrix, and we compute the difference A minus S. Next, we define the following matrix omega 1. Okay, this is this matrix has all columns and m lines. Next, we solve the system of linear equations. Omega 1 xi equals fi. This is why, because I would like to find a matrix omega 2 such that A equals omega 1, omega 2. And fi are the columns of fi. So under some conditions on the number omega, which is unlimited, so we prove that the columns of the matrix omega 2 are unlimited. This is the solution of the system W1x equals f, and finally we show that the matrix F can be written as the product of two unlimited matrices. As an application, we take this matrix, okay, which is limited, and we take S by this matrix. S is non-zero, and this is the difference A minus S, okay, and define the matrix omega 1. Okay, here A, M, N, 3, 4, and omega 1, 3, 5. So we take L equals 5. This is L, L minus 1, and here L minus M minus 1. Okay, as in the construction of omega 1. Okay, L, L minus 1, up to L minus M minus 1. Okay. After solving the system of equations, we obtain the matrix omega 2, which has unlimited columns. This is the first column, the second, third, and the fourth. Okay. So F equals omega 1, omega 2, and A equals S plus omega 1, omega 2. Let M be an unlimited matrix given by this expression. Here, the matrix A1, A2, up to AK are all limited. And we assume further that these matrices are pairwise commutes, okay, as this. And the exponents N1, N2, and K are all unlimited. So this matrix N can be written as the sum of a limited matrix S and the product of two unlimited matrices, omega 1 and omega 2. For the proof, I think it's the same for a result with integers. We consider the exponents are all even, and when they are all odd, and the last case when some of the exponents are even and some others are odd. Okay. For further research, we consider the following matrix forms. So in the first, we assume that the determinants of omega I and the determinants of omega j are of the same order. Okay, S plus the product of K unlimited matrices. In the second form, we assume that omega 1 and omega 2 are commutes. Okay. In the form 3, we assume that S is given by Ki, where I is the identity matrix. And in this form, omega 1 and omega 2 are given by omega transpose. So omega 1 equals omega 2 transpose. And in form 5, we add the condition that omega 1 or omega 2 is idempotent or nilpotent. And in form 6, A equals omega 1, omega 2 plus omega 3, omega 4, where omega 1, omega 2, omega 3, omega 4 are all unlimited, but we add the condition that determinant of omega I and the determinant of omega j are of the same order. Finally, we talk about the integer of Gaussian, the ring of Gaussian integers, z of I, which has the same properties as the ring of integers. We need to define an unlimited Gaussian integer when the norm of z is unlimited. Okay, and we need to define completely unlimited Gaussian integer when the real parts and the imaginary parts are both unlimited. Okay, and define a Gaussian integer completely unlimited with limited difference when x plus y or x minus y are is limited. So if either x plus y or x minus y is limited, we say that z is completely unlimited with limited difference. And here define Re unlimited Gaussian integer when the real part of z is unlimited, but the imaginary part is limited. And the converse with I am unlimited Gaussian integers. We define two Gaussian integers, omega 1 and omega 2 are of the same order. We say that omega 1 and omega 2 are of the same order when the norm of omega 1 over the norm of omega 2 is appreciable. And we use this notation when the real parts of omega 1 and the real parts of omega 2 are of the same order, and the same for the imaginary parts. We use this notation. We say that a Gaussian integer is even when 1 plus I divides z and odd otherwise. Okay. We have this theorem. So every unlimited Gaussian integer can be written as the sum of two unlimited Gaussian integers having the same order. For the proof, we use the properties of Gaussian, of odd and even Gaussian integers, and we use the relation between integers and Gaussian integers. Okay. In this corollary, we have z to the k, z to the power of k, and k here is odd. So if k is odd, then z to the power of k can be written as a unit plus omega 1, omega 2, where omega 1, omega 2 are two unlimited Gaussian integers. The proof is quite simple. Here, the unit -1, and when k is equals 40 plus 3, we have these expressions, and when k equals 40 plus 1, we have these expressions. In this theorem, every unlimited Gaussian integer z equals x plus iy with y is even can be written as the sum of two squares in Gaussian integers, where omega 1 and omega 2 are of the same order. In the proof, assume that omega 1 given by c plus di and omega 2 is a plus bi. Okay, and z are, of course, x plus iy. We find the relation between a, b, c, d, and x, and we find that y is even. So if x is of the form 40 plus 2, then y is divisible by 4. Here we distinguish 4 cases. In the first case, when x is odd, and of course y is even. And in the second case, we assume that x is not divisible by 4 and even and not divisible by 4. And y is divisible by 4. Okay, we find that omega 1 this number and omega 2 this number. In the third case, we assume that x and y are both divisible by 4. And in the last case, we assume that x is divisible by 4 and y is even, but not divisible by 4. In all cases, these cases, we can write z as the sum of 2 squares, omega 1 squared plus omega 2 squared, with omega 1 and omega 2 are of the same order. Okay, look at this. For example, in this omega, this is the real part, and this is the imaginary part. But the imaginary part is u prime plus v prime. Okay. Finally, we have some questions in this topic. This is a general problem question. Okay, we don't know if every unlimited Gaussian integer can be written as the sum of a limited integer and the product of 2 unlimited Gaussian integers. And also, we don't know if there is an unlimited Gaussian prime, unlimited Gaussian prime, okay, P, such that for any limited integer s from z of I, we have P plus s cannot be written as the product of 2 unlimited Gaussian integers. In the second question, we ask if every unlimited Gaussian integer can be written as omega 1, omega 2 plus omega 3, omega 4, where we add the condition the norm of omega I over the norm of omega j are of the same order. The norm of omega I over the norm of omega j is appreciable. In this question, we ask if this number 1, 1, 1 n times and plus 2, 2, 2 m times here, and n and m are unlimited. So we ask if z can be written as s plus omega 1, omega 2, where s is a non-zero limited Gaussian integer and omega 1, omega 2 are 2 unlimited Gaussian integers. And in the last question, we ask if every unlimited Gaussian integer can be written as units plus the product of 2 unlimited Gaussian integers. And there is a good question. Who are the biscuits of number theory? And many thanks to the organizers, and thank you very much for your attention.
Okay, thank you, Bellaouar.
Okay, thank you.
Let's thank our speaker, and I apologize for the child that's speaking in the background.
Yeah. Well, may I ask a question?
Yes, Ken, go ahead.
Hi, sorry for the video problem, but I'm this handsome elderly gentleman. Anyway, this is this is exciting the way that this kind of work. But The original, invention of the imaginary numbers was exciting. Just seems to be in a world almost of science fiction here. It's very. But does this two sort of minor? Do you find that working with these unlimited numbers and whatnot, you get alternative proofs of classical results for the finite, the usual finite numbers?
Okay. In standard mathematics, so sometimes I have problem with sufficiently large. If we take n sufficiently large, we can write a sufficiently large integer as the sum of a small number plus the product of two sufficiently large integers.
Mm-hmm. Ah.
Okay.
Mm-hmm. But does this work raise other? Does it lead you to new questions about the standard numbers, about the things about the standard numbers that would be helpful in working with unlimited numbers and etc.? I mean, does it lead to open questions about the standard numbers?
Open questions about
the usual standard numbers, the limited numbers.
I didn't understand your question very well, but
let's say, is there a theorem that's not proved about ordinary integers that would be helpful in working with in the context you're working in, with the unlimited numbers?
So in this topic, we give the properties of unlimited integers.
Mm-hmm.
For example, we know that there are infinitely many primes. So in the non-standard language, there is an unlimited prime number. Also, by using the prime number theorem, if Pn is the nth prime number, and so Pn over Pn plus 1 tends to 0. In the non-standard language, we mean by this writing that Pn and Pn plus 1 are of the same order. That is, the ratio Pn over Pn plus 1 is appreciable.
Ah, interesting. Thank you.
Okay, thank you very much.
Wow.
Oh.
My apologies. I had to step away for a second because of my son. Are there other questions?
Well, perhaps I could say something about Ken's question. Yeah, there is actually some problem that Djamel posed that is equivalent to some version of the kind of conjecture about quadratic forms, whether a quadratic expression can have infinitely many prime values, which is unsolved. I don't have it in my head now to tell you exactly what the problem is and what the equivalent form is, but there is an example of a problem that would require a new result in classical number theory to be solved. Yeah. Then I have also a question about, you mentioned these different forms, F1 to F6. So are there results about what matrices can be expressed in those forms, in particular the form F2, where the two factors are commutative? Do you have results, or are these just sort of general open questions?
No, I have no results for these forms, but in the future, I'm going to study these types of
I see. Yeah. So Right. So as of now, it's open. Yeah. And so, if I may ask, what motivates these questions? Is it just basically things that you
No,
find
this is
interesting and can do, or is there some deeper motivation?
In the study of matrices with integer entries. There are several problems about the factorization of any matrix with integer entries as the product of idempotent matrices or nilpotent matrices. I think this problem is the same with integers. This is the factorization.
Yeah. Okay, well, thanks. I think the talk gave a good
thank you.
idea for what you're doing. Yeah.
Any other questions? Okay, let's thank our speaker again. Thank you.
Okay, thank you.
And I'll mention next week we have Bartosz Cishwo from Gdansk, who will be speaking on satisfaction classes with the full collection scheme, which at the same time. So and as always, the same link, same time, and this talk will be posted on the YouTube page. So I will see you all then.